Hello, welcome to Math 112, College Algebra and Trigonometry. So for the first day, we just kind of went through the syllabus, which you can go ahead and read on the LMS if you'd like. And then we started section R.1, which is dealing with sets here. So to start off, just the definition. So a set is just a collection of objects. It could be a collection of any object. For example, if you did a set of a class, you could have the different students as objects in that set. Most of the time in math, when we talk about sets, we're talking about sets of numbers. So most of the time we're going to be dealing with sets of numbers there. The objects that belong to a set are called the elements or members of a set. So for example, again, if we use the class example, if we have a set of students that make up a class, then each of the students would be an element of that set or a member of that set there. Sets are commonly written using set braces. So again, you can write a set just by starting off with set braces, and you can just list the members of that set. So I'll just start off with 1, 2, 3, and so on and so forth there. And then you can go ahead and close off your set braces once you're done listing the elements. To know whether something is a member of a set or not, we use the symbols. So this little E stands for element of or member of a set. And then we have the little E with a strike through it. That means that it's not going to be an element or member of that set there. So for example, if I call this set A, the number 1 is an element of set A. However, the number 4 is not going to be an element of my set A there. If a set has an unending list of distinct elements, it's called an infinite set. So if you can't possibly list all the elements of a set, then it's said to be an infinite set there. And then a finite set is one that has a limited number of elements. So if you can list all the elements of a set, then it's a finite set. If you can't possibly list every single element, then it's said to be an infinite set there. Alright, so the first example we have here is you want to identify each set as either finite or infinite, and then determine whether 8 is an element of that set. So for set A, so for part A there, I'm just going to call this set A here. So we have 1, 1/2, 1/3, 1/4, 1/5, etc. there. So we just have 1 over each of the different natural or counting numbers. So the counting numbers are the natural numbers. Are those numbers 1, 2, 3, 4, 5, 6, and so on and so forth. Alright, so first of all, we want to determine whether this is a finite set or infinite set. So since the list of counting numbers or natural numbers is unending, meaning it never ends, go figure, this is going to be an infinite set. Infinite set. Generally, if you have a set that ends with this ellipsis or these 3 periods here, generally that's going to be an infinite set, because you're not going to be able to find the last element of that set there. And the second part, we were asked to determine whether 8 is an element of this set. So since we can't write 8 as 1 over some number, some natural number, 8 is not going to be an element of my set A. And then for part B, so we have x, such as x is a natural, or again a counting number, between 7 and 9. I'll move my paper up here a little bit. Alright, so I'm just going to call this set B here. So B is going to be the natural numbers between 7 and 9, which in this case there's only one counting number in between 7 and 9, and that's going to be 8 there. So the elements of my set B are just going to be the single value 8. Alright, so since this only has one element in it, which means we can write down all the elements in this set, this is going to be a finite set. And then since 8 is the only element of a set, we also have that 8 is an element of my set B there. Alright, so some other definitions. So when discussing a particular situation or problem, the universal set, whether expressed or implied, contains all the elements included in the discussion. Most of the time, if it's expressly stated what the universal set is, we generally denote that by the letter U. And then we list the elements of the universal set. Otherwise, it might be implied by the problem and the situation there. The null set or empty set is a set containing no elements. It's denoted either by the symbol, so you have 0 with the little strike through it here, or you can just have the set braces with nothing inside of them. So that represents the empty or the null set, which is just the set that contains no elements. By definition, set A is a subset of set B if every single element of set A is also an element of set B. We generally denote this by A, and then this is what this is the subset symbol. So you have A as a subset of B. So if every single element in A is also an element of my set B, then it's going to be A is going to be a subset of B. By definition, every set is a subset of itself. Every set contains the elements that are in itself there. Also, by definition, the empty set is a subset of every single set there. And then two sets are said to be equal whenever A is a subset of B and B is a subset of A. So if both those statements are true, then the two sets are said to be equal. Another way of thinking about this is A equals B if two sets contain exactly the same elements. So if every single element of A is also in B, and vice versa, every single element of B is also in A, then the two sets are going to be equal. Alright. So if we let U equal the elements 3, 9, 15, 21, 27, 33, and 39. And A equal the elements, so we have 3, 9, 15, 21, 27, and 33. And we're asked to determine whether each statement is true or false on there. So the first one, so A is a subset of U. So if you look at our two sets, so every single element in set A is also an element of my set U. So A subset of U. So this statement is true. Again, since every single element of my set A is also an element of my set U there. And then for part B, so we want to determine whether the statement U not equal to A, we want to determine whether that's true or false. So again, in order for these two sets to be equal, A has to be a subset of U, so that means every single element in A has to be an element of U, which the previous problem, we have that. But also, in order for equality, U also has to be a subset of A. So that means every single element in my set U also has to be in set A, which if you look at that last element, that 39, so that 39 is an element of my set U, but is not an element of set A, so that means that the two sets are not going to be equal. So in this case, that statement is also a true statement. Operations with sets. So if you let A and B be sets with the universal set U, the complement of set A is a set of all set A complement, that little apostrophe. That means when we're talking about sets, that means that we're dealing with complement. So the complement of set A is a set of all elements in the universal set that do not belong to set A. So another way of writing that in set builder notation is we have the complement of A as all the elements X, such that X is an element of my universal set, but X is not an element of my set A. So you can find the complement by listing all the elements of your universal set and then just crossing off the elements that are in your set A there, or whatever your set you're trying to find the complement of. And then the leftovers, that's what's going to be the complement of that set. The intersection of sets A and B, written A and then this upside down U, that stands for intersection. So A intersected with B is made up of all the elements belonging to both set A and set B. So if you have something that's in both set A and also in set B, then it's going to be in the intersection of the two sets. And then the union of sets A and B, written A, U, B. So that U, that stands for the union there. So you have A, U, B, union B is made up of all the elements that belong to either set A or to set B, or both. So another way of writing that in set builder notation is we have A union B equals all the elements X, so that X is an element of A or X is an element of B. So if it's in either set, then it's going to be included in the union there. Alright. So if we let U equal the numbers 1 through 9, so we have 1, 2, 3, 4, 5, 7, 8, 9. A is going to be the even numbers, so we have 2, 4, 6, 8. And then B is going to be the multiples of 3, so we have 3, 6, 9. Alright? And we're asked to find the following sets. So the first one, we want to find the complement of A. So again, you can find the complement by listing all the elements in your universal set. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then crossing off all the elements that are in your set A. So the complement is everything in the universal set except for those that are in the set that you're taking the complement of. So in this case, we have 2, 4, 6, 8. So then the complement of set A is just going to be all the odd numbers. So we have 1, 3, 5, 7, 9. For part B, we have A union B. So the union, again, is everything that's included in either set A or set B here. So in this case, we have 2 is included in set A, 3 is included in set B, 4, 6 is included in both, 8 is included in set A, and then 9 is included in set B. So the union is going to be all of those. So for part B, we have the intersection of A and B. So that's going to be everything included in both sets A and set B. So if you look at our set A and B, the only element that they have in common is this element 6. So the intersection is just going to be the single value 6 there. Alright. The complement of the empty set. So for part D here, so you want the complement of the empty set. So again, to find the complement, you just list all the elements in your universal set. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you're going to cross off everything in the set that you want to take the complement of. So in this case, the empty set doesn't contain any elements, so we're not going to cross off anything. So the complement of the empty set is just going to actually be the universal set. And then the complement of universal set, again, you start off by writing all the elements in your universal set. 2, 3, 4, 6, 7, 8, 9. And then you cross off everything in the set that you're taking the complement of, so everything included in your universal set, which is everything there. So all you're left with is no elements, so the complement of the universal set is going to be the empty set there. So the complement of the empty set is